title of today's talk, which is nothing but transforming text-to-speech technologies for Indic languages and evolution framework, and we also cover few industry applications. So before going into the topic, I just wanted to give you a glimpse of what all things will be there. A brief overview of what TTS is, text-to-speech synthesis is, and how it has evolved, and from where it has started and now where we are. A brief evolution part, and what are the core components which are needed for building a basic TTS system, and what are those components which were needed extra to build the state-of-the-art TTS systems. We go on through those core components, and then in order to build these state-of-the-art techniques, as Samudra sir has already mentioned, data is all we need. How much data is depending upon the architecture and the target language which you wanted to train the models for. So we go a brief dive over the data preparation pipeline which was followed or which are being followed in the industries. Then there are several architectures, as I have told, with this evolution over deep neural networks and all, there are several architectures have come. I'll be taking one example of the state-of-the-art architecture, and I'll be explaining you, which is called style TTS framework. And then how we evaluate the traditional TTS systems and how different it is in modern TTS systems where the challenges arise. So that is where the challenges and the proposed evaluation metrics also comes into picture. Then a few use cases. Yeah, so let's begin with text to speech. As you have, I mean, the name itself speaks for it. We just try to convert the written text into spoken format. So whatever you write, we wanted the machines to speak for us. So that is where the text to speech systems are all about. And there are key applications like you might be seeing, right? Your IVR systems, content generation. These days, lot of YouTube videos where the human is not speaking, but the content generations are being happening. And there are voice assistants and several key applications are there, right? And yeah, as I have already told, there are two major building blocks in the traditional TTS systems. One is analysis pipeline, where you get the text and process it, convert it into the text to speech model readable format. And then the second module is synthesize, in other way, speech generation module. So text preparation and speech generation. And each of these components are again subdivided, which we will be deep diving in. And yes, the main challenges are, I mean, again, just to extend what Samudra sir has already told, there are a lot of complex linguistic structures within the language. There are a lot of similarities within the same language, but if you hear, they are completely different. And at the same time, there are a lot of linguistic features which were completely different. But if you listen to them, the acoustics, you feel, array, this language is what somewhat related to my own language. So there is a lot of complex linguistic structures, diverse phonetics. So because of these two challenges, we really need a high quality data set, at least to train the text to speech models, because these are completely data dependent. So these are few challenges, and how we overcome it is what we will be seeing. So yeah, at a high level, in order to develop Indic TTS, we need a robust architecture which captures all the data variations. We need robust data resources and a thorough performance evaluations, because a sentence in one language or a suppose, let me take an example. If I give you a Hindi sentence, a South Indian person might say that, yes, this audio is properly pronounced. But when a North Indian person comes and says, no, it's not in my accent, it might be a different accent, it's not a proper Hindi. So these linguistic variations are also need to be thoroughly evaluated. So these are the challenges which we will be discussing on how the solutions are being proposed. Yeah, uh, I think this is disturbing, right? Let me minimize. Is it visible now?
Yes.
Yeah. So yeah, so the evolution, as we have can see, it has started in late 90s, where they initially started it with something called Voder. So it is completely mechanical. There is nothing electrical, or machine doesn't do it for you. So basically, you have a resonator setup where a manual typewriter kind of setup is there, and your excitations, right? Whatever excitations were there, you just before going to excitations, let me introduce you speech production system, because without that, I think you will not be able to appreciate what order is. So you have a resonator. Let us assume that that resonator is a vocal tract and nozzle cavity, and you have an excitation source, which is
Sriram,
nothing but
you are in evolution slide actually.
yeah, yes, sir. I'm just giving an introduction. I don't
Okay.
have a slide for that. I'm just giving them the
Okay.
philosophy. Hello?
Please continue.
Yeah. So your vocal track is what your resonator is, and your excitation is what your glottal vibrations, whatever vibrations are coming from your glottis, right? So now they have tried to attend this in a mechanical way, where your keys are your resonators, and there is a pedal at the foot which creates your excitation. So I just had a small video. Let me play this video. Machine uses only two sounds produced electrically. One of these represents the breath, the other the vibration of the vocal cord. So basically, these are two different types of excitations. One is voiced, where you can see this oh kind of thing, right? And the other one is breath, the white noise kind of excitation. So even in humans, we have these two kind of excitations. There are no phonograph records or anything of that sort. Only electrical circuits, such as are used in telephone practice. See how you put expression into a sentence. Say, he told me, no expression. Now say it in answer to these questions. Who saw you? She and me. Who did she see? She and me. Did she see you or hear you? She and me. So, did you understand what exactly is happening behind? So, a person is trained to adjust your resonating frequency. Love blossoms. Hello? Memories are crafted. So, and happiness resides. Yeah, so basically a person was trained to play with those keys and generate different resonating frequencies, and this is completely manual as you have seen in the video. So based on the context, the person is actually generating the resonating frequencies and she's actually providing the excitations to produce the sound. So these are the initial TTS developments which were completely mechanical and manual. Then in 1983, the second variants have come, Deck Talk. So what they do here is they try to replicate with the invent of these IC chips and all. Instead of manual, why can't they configure everything as an electronic circuits? So that is the major jump where these electronic circuits have come. And still here, you haven't modeled anything in speech. You have hard-coded the resonating frequency, saying that if I enter these characters, you have to select these resonating frequencies and generate the sound with the given excitations. Then the in 1990s, they actually started playing with the speech sounds. So the first one is concatenative speech synthesis. Here, what they do is they just try to, for example, if I take an English language, they try to identify all the basic sound units, which we call as phonemes here, right? All the phoneme sound units they try to gather. They have a dictionary, like ASA dictionary, which you have seen earlier, right? For each word, you have a phone sequence. So they have collected all these phone sequences, and for these words, they know that these are the phone sequences. And corresponding to each phone, they have also recorded a sound, whatever sounds you are reading here, right? So now, whenever you type that particular word, they start stitching these words. I mean, the phone units. So that is how this concatenative speech synthesis has started in 1990s. And yes, then with the advent of GMM, HMM, or the sequence modeling techniques in 2000s, each of this phoneme unit, now they started training using a distribution model using GMMs, and the transition they have started learning using HMMs. So that is where this GMM HMMs have come to train your acoustic model. So this is where the acoustic modeling or the speech modeling have started. So far till late 90s, if you see, there is no modeling involved. Only behind the philosophy, they are either trying to tweak the format frequencies, or they started converting the phones by concatenating it. And then in 2000s, they started training the model. So, and the first TTS model was GMM HMM based model. And yes, and since then, with the advent of our deep networks, there are a lot of architectures which have come across, like Tachytron 2, fast speech, VITS, style TTS, and now style TTS 2, Kokoro. You might be already aware the recent architecture is Kokoro. So there are a lot of architectures which we have come, and the trends are like on a daily basis, a new architecture starts pumping in. And in this talk, we will mainly focus on the style TTS, the architecture, how this architecture is different from other TTS, and how this can actually help us to better understand Indian languages. Yeah. So the main core components are in the traditional ASR engine, as we have, sorry, traditional TTS engine, you will have a MEL model. MEL model in the sense, whatever text you have. convert it into speech representation, your MEL spectrograms. So given a text, this model is trained to generate a spectrogram, and there is a vocoder which converts the spectrogram to voice. So these are the two building components of all traditional TTS models until the style TTS have come in. So they just given a text, they convert it into MEL, and you can train a vocoder separately where MEL is the input and speech is the target, and you have to train a vocoder. And upon concatenating these two models, given a text, you get the voice as an output. But yeah, and G2P is also an integral part. Why we need G2P? I think by now you should be already aware of it, because graphemes are nothing but characters which are in written format. Phonemes are in spoken format. So in writing, for example, if you see the given text, the ka sound can be written in multiple ways: C, K, CK, QU, CH. So all these multiple variants corresponds to a single sound. That is phoneme, ka, right? So representing the graphemes in phonetic sequence actually reduces lot of computations, lot of targets to be trained, and lot of confusions, right? So that is where converting, in other words, if I can say, converting writing formatted text to spoken formatted text is what grapheme to phoneme conversion does. Yeah. So these are the three building blocks until now. But now, with the advent of uh, what do you say, transformer architectures, we can actually capture the details more than converting text to speech. What are those? Nothing but prosodic features. How long a word or how long a phoneme has to be spoken. Duration modeling can be done. Pitch. How much pitch I want across each word. That customization of pitch selection. I want this to be spoken with low pitch. I want to be spoken the sentence with high pitch. Style, with what tone, whether I have to speak the sentence in an angry mood, whether I have to speak the sentence in sad mood or surprised mood, or do I need to write it like a news anchor? Do I need to read it like a advertisement girl? So those are different styles, right? So we can even try to model those styles. And stress. So there are words where you need to emphasize, right? You just keep stress. So where to put stress, where not to put stress. So all these are in detail with respect to a single audio file. What all things can be extracted comes under prosody. Apart from the speech features, I mean the MEL model, which is trying to capture the sequence to sequence model. Apart from that, prosodic features are some high level features which are corresponding to that particular speaker. So the new architectures try to address this fourth block because the other three are already solved. So now comes this fourth problem. So that is the advantage and that is the challenge, because now, yes, you have created, but how do you evaluate? What are the tools? How do you actually evaluate? How good can you say that this particular audio file is better than this particular audio file? Because this is a generative architecture and it is completely based on subjective analysis, right? Yeah. So now let's go to the first part, which is called text corpus or the data preparation, which has both text as well as speech. So the basic flow which we have adopted, at least in Reliance, is first we have to go and obtain a lot of text data which was available on web resources from different sources. Because as I have told, I need to capture style from different variations. So I need to go to news blogs, capture news. I need to go to advertisement. I need to go to movies, extract subtitles. I need to go to different domains uh, like NPTEL lecture videos. I have to generate from the podcasting videos. So we have to go to different areas to capture different styles or different prosodic features, crawl those kind of text data, and then perform basic text normalization like removal of characters, abbreviation expansions, converting numbers which were written like 1, 2, 3. Because as I have told, we have to convert the written format to spoken format. You have to convert the numbers to words, handle date, times, units, case sensitive. We have to remove the case sensitiveness because we don't want our model to learn separate phonemes for capital L and small l, suppose. So all these text normalizations has to be done. And once this text normalization has done, how do you ensure? Because see, now this data is huge and I can't record this entire data, right? How do we select the text data in an optimized way so that we can give a limited set of data for training, right? That is the next challenge, because now gathering the text data is easy. But now once we have to go and collect the speech data, we can't record this much of data, right? Because TTS, again, it depends on a single speaker, right? I have to collect this much of variations and this much of data per speaker. So at a ground level, if you say, we benchmark TTS models by collecting around 20 hours of speech. Now, how do I select the text data which gives me 20 hours of speech is the challenge, right? So for that, what we have done is we have converted all these text normalized text, whatever normalized text we have, into phoneme sequences, then clustered them into triphones, and then went for a phoneme distribution, right? So now, once you go to triphones, then I mean, for example, if I take English language, you have around 64 phoneme sounds, and when you convert that to, when I say 64, including full stop, commas, and all, and then when you go to triphones, we have modeled around 2500 or 2700 triphones. Now you go and plot the distributions of triphones and try to collect those sentences which has reached certain threshold. Let's say, for example, you have to select sentences in such a way that the least phoneme has at least seen 100 times. So now, until you see that 100 times, you start screening your text data, right? And once you see that, yes, my text data has crossed this limit, the rest all data can be pruned. At the same time, I also keep an upper threshold. I don't need beyond that. This is what is called data biasing. I don't want to get either my model to get biased to one particular domain by taking lot of examples from that particular triphone, or I don't want my model to underfit where the data is very less. I don't want my model to underfit. So you have to go beyond this threshold, and at the same time, you should not go beyond this threshold. By putting this criteria, we iterate the model in such a way that it selects the text data which satisfies this division. And then this is gone to the data recording studio where the agents, as I told, a single male and a single female agent goes and starts reading this audio file in whatever style it was mentioned in the text data. So this is the data recording pipeline and a small screenshot of the triphone distributions. If you see, this is the triphone distribution. Whatever you are seeing on the left side is on the entire corpus without pruning. And the right side one is the triphone distribution plot after pruning. So we can see, right, lot of right hand sides, you can see lot of peaks. That is because of this algorithm, which actually selects the sentences beyond. I mean, the left and right is, I mean, left again, I forgot to mention that this is randomly selected sentences which corresponds to 20 hours. And the right one is algorithm based sentence selection. So you can see, right, the lot of peaks are coming up and it is not beyond 0.2% distribution. So this is the distribution plot. And then, yes, as I have suggested, now once this is done, we try to collect the speech data by ensuring that you capture the prosodic features, collect different dialects. As I said, you have to speak that Hindi in native North accent, South accent, and a Malayalam candidate might speak Hindi differently. So we wanted to capture all these dialectic variations. And then, yes, code switching, where English words are actually being mixed in Hindi, not just Hindi. In India, majority of native speakers actually mix one or the other language. For example, if it is Hindi, we mix English. When comes to Telugu, we mix Hindi and English to Telugu. So there are lot of words mixed from other languages, which we term as code switching. So we wanted to even cover that because in realistic examples, those are the scenarios which we need to address. Yeah, so with that, our data generation pipeline or data creation pipeline is done. So I have collected text data, I have selected the text data, and then using the text data, I have recorded in such a way that these are the features which need to be covered. Then what? Yeah, next goes to the training pipeline. So as I have already mentioned, Style TTS framework has three major advantages when compared to others. One is transferable monotonic aligner. Just for time being, let's pause here. I'll be explaining in detail, but for time being, understand the terminologies. Transferable monotonic aligner. You're just trying to transfer the learnings which were done by monotonic aligner to your TTS engine. That is what is transferable monotonic aligner. Self-supervised learning based style encoder. So you have an encoder which learns the styles which we have discussed earlier, different styles using self-supervised learning technique. And then duration invariant data augmentation schemes, because now you have trained your model with a normal pitch or normal speed, and tomorrow someone has given a sentence and ask it to generate in a bit faster way, your system should be able to generate that without any variations in your pitch or the speaking style. Yeah, so this is so basically that style TTS training happens in two different stages, stage one and stage two. I'm not going into much technical details by putting all math, but let me explain you the philosophy. So the blocks which you are seeing, right? There is a text encoder which takes phoneme sequences which were converted from text. convert them into hidden representations, text embeddings, and then you have a MEL spectrograms generated while training for the corresponding phone sequence. So this text aligner, in other words, we can call it as an ASR engine as well. So this text aligner, you have taken a pre-trained text aligner model and then use these phone sequence along with the MEL spectrogram and start aligning your data. Alignment in the sense, your speech should be actually aligned with your text. And then this is a style encoder, which is a free running encoder, which takes the MEL spectrogram and starts learning the variations apart from the things which were captured in this text aligner and pitch extractor. And yes, pitch extractor is something which extracts your pitch contour and energy contour from your MEL spectrogram. So apart from pitch, apart from energy, apart from your alignments which were generated from ASR, which is nothing but the phonetic representations, what extra is there is this style encoder which is being trained, I mean, which it is getting trained to. Because if you see the final decoder's loss function gets minimized only when all these four losses gets minimized, rather the three losses, right? The basic TTS loss, which is your MEL model and your vocoder model, and then your style encoder loss and your pitch extractor loss, right? So unless these three losses gets reduced, your decoder training keeps on going on. So that is where your style encoder is trained using self-supervision, where such self-supervision is coming from these things. So I have trained this, I have trained this, I have trained this. Now, in order to loss get reduced, you have to capture the other variations, is the command which this style encoder is getting. Yes, and now the first introduction to the transferable monotonic annihilator in the style TTS. So what does this actually mean is in the other approaches like faster speech, other approaches which we have seen, right? So what they do is they take a non-trained, I mean non-fine-tuned version of ASR engine directly. For example, if I'm training a Hindi TTS engine, I take the existing Hindi ASR model because I'm not able to fine tune or I don't have fine tuning data. I take that pre-trained model, put it, and then start generating the alignments without fine tuning using your phoneme sequences and your speech data. So if you see here, there are a lot of noises, right? And then the middle part, if you see here, you don't have any pre-trained ASR engine. Rather, you are training your own ASR engine on this 20 hours of TTS data. So what happens here? You can see a very clear peak and there are a lot of discontinuities, right? Here there is a discontinuity, here there is a discontinuity. This is happening because your model has been trained on the 20 hours of data and it is able to exactly train the data, but it is not able to generalize. So it has actually overfit the model. I mean, overfit the data. So this model are sharp and discontinuities, which says that the models are actually, I mean, the model is actually getting overtrained or overfit to your training data. So that is where style TTS comes in. And what it does is it takes the pre-trained model, this model, it puts into your training framework as we have seen here. So this text aligner is nothing but your pre-trained model. Put it here, and then you train that STT model alongside your TTS phoneme model, style model and all. And then if you see this engine, for the same phone sequences, your model, style TTS, is able to generate a better alignments when compared to the pre-trained model or the monotonous trained model. Right. So this is their first contribution towards style TTS framework, where you can generate an accurate alignments. Yeah. And then style encoder. So basically style encoder is a simple feed forward, but the major difference is like unlike traditional feed forward architectures, it uses residual connections. Residual connections, or other way we can call it as skip connections. So you have a connection from the previous layer to the next layer directly. So that is where it has its own advantages, like you have a better gradient flow, your training efficiency increases, and then the overfitting actually reduces, convergence will become faster, and you can actually reuse these features because you are directly passing this. And since you are getting an access to the direct features because of the skip connection, your overfitting is also, I mean, your gradient descent or vanishing gradient problem, you can say, can be handled very efficiently. So that is where your style encoder has this feature. And then, yes, coming to stage two, now that your aligner has trained, you use that aligner and generate the alignments. And using that alignments, you can actually predict the durations. So now why can't we actually put the duration predictor also into stage one? That is the question one, right? Why? Because unless we have trained the aligners, aligners in the sense, I don't know how much this phone sound has been spoken, how much time the phone E has been spoken, right? Unless that alignments are not trained properly, I'll not be able to get this duration. Duration matlab how many frames are coming from sound A. That is the duration. If you see here, the red color corresponds to one phone, green color corresponds to one phone, blue corresponds to one phone. So this x-axis is what that duration predictor is trying to capture. And once that is done, you are actually going and again predicting the pitch and energy, because now you have an accurate uh, alignments generated. So that is where your stage 2 has been decoupled from your stage 1. And you learn your alignments, you learn your pitch extractor in stage 1. And using those alignments, you actually predict duration and prosody in the second stage. Yeah. So now the third contribution is duration invariant, as I have told. Now what they do is, instead of taking that monotonous data, whatever was collected of 20 hours from that speakers, whatever I have said, right? So in order to capture the speed and slow variations, we synthetically reduce the speed by certain threshold, and we actually make the same data spoken faster by certain threshold. So delta minus and delta plus, and now you have generated a threefold data, right? 20 hours became 60 hours. Now use this data to train your model. So that is where it becomes duration invariant. So no matter how you want, the same text data has actually seen three variations in the data: slow, speed, and medium, right? So that is the third data augmentation technique which was incorporated in this training pipeline. And yes, now I think so far this is with respect to the training pipelines. And now what we have achieved. So now you can see I'm taking an example of Tamil language.
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
Is it audible? Can someone confirm? Hello?
Yes, it is audible.
Okay, great. Yeah. So now if you see, for the very same sentence,
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
yeah, so here the requirement is given a same sentence. I want it to be in a happy mode. Now for the same sentence, I can generate a sad mode.
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
Now for the same sentence, I can even generate an angry mode.
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
So this is one good thing which had happened with respect to style TTS. Not just transferring text to speech, but you can also transfer emotions, transfer styles, right? So this is step 1. What else can we do? We can actually try to capture someone else's style. So now you just give me an XYZ speaker who is not there in my training. Just give me, and I want to generate that particular TTS output in their style. So in other ways, you want Amitabh Bachchan to speak like Shah Rukh, but the voice should be Amitabh Bachchan's, right? So let me put some example. I have taken some Alia Bhatt ka Hindi example.
अम्मी सुनो तो, मेरे को बस अपनी रिस्पेक्ट वापस चाहिए और आपकी भी. इनके साथ वही करूंगी डिट्टो जो ये मेरे साथ किए.
So you can see, right, this is an Alia Bhatt who is speaking Hindi, but my intention is to capture that Alia Bhatt's Hindi style and transfer it to the very same Tamil TTS.
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
Right, and now this is a news reading style.
और हम शुरुआत कर रहे हैं विलेज डिफेंस के उन कर्मवीरों के साथ जिन्होंने अपने हाथों में ये जिम्मा ले लिया है कि इस क्षेत्र में देश का कोई दुश्मन दाखिल नहीं हो सकता.
Yeah. So now
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
we have even experimented with some in-house audios.
जी, आपके लिए जियो सिनेमा खोला जा रहा है.
நான் இன்று காலை எழுந்ததும் பச்சுத்தி செய்து காஃபி அருந்தி பின்பு வேலைக்கு செல்ல தயாரானேன்.
So yeah, so what this demonstrates is I don't need to be speaking Tamil itself in different styles. You can give me a reference from any language. Our model has to actually extract that style. So that is where the style encoder block, which we called as a self-learned encoder, right? It actually has learned in a self-supervised way where it is trying to capture the other variations in the data apart from the speech information, which is nothing but your phone sequences, right? So that is where when you give this reference to your style encoder, it is trying to capture everything else apart from the phone sequence, while your TTS model is trying to capture your phone sequence data. So that is where your styles with I mean, independent of language are being actually transferred, right? Yeah. So now challenges with respect to single speaker. So now with coming requirements and coming business use cases, now people will say, I just don't want you to speak like an Alia Bhatt, or I just don't want Amitabh to speak like Shah Rukh Khan, but I want Amitabh Bachchan itself speaking for my advertisement, right? So I want Amitabh Bachchan's voice with Amitabh Bachchan's style. But now I have TTS trained for 20 hours of one speaker, right? So I have a capability only to transfer his style to my voice or my TTS voice, but I am not able to train 20 hours of Amitabh Bachchan's voice. Yeah, you can do by collecting all web resources, cleaning and all, but that is a different story. And tomorrow someone will come and say, hey, I want my voice to be spoken in TTS, right? So for that, there is an architecture, again, the same style TTS framework. Now the same style TTS architecture, instead of giving single speakers 20 hours of data, what we can do is you take around 400 to 500 speakers, or you take directly the ASR data itself, whatever data you have. Only restriction which you need to keep is the transcription quality should be correct. Transcription quality in the sense, whatever was spoken in the audio, you need to have a proper punctuated text data. That much you need to ensure. And the second ensuring which we have to do is each speaker's data need to be from minimum 10 to 15 minutes. Let's take that multi-speaker data and then train the multi-speaker style TTS framework, right? So that is what we have done in our experimentation. We have taken around 400 Hindi speakers ASR data, and we have taken that in such a way that each speaker has at least 10 to 15 minutes of voice. I'm sorry. Yeah, each speaker has taken around 10 to 15 minutes of voice, and then we have triggered the same style TTS framework, right? And now here you can see that I have given two blocks. I'll come to this later on. But if you see here, now what we are doing is to this multi-speaker framework, what I am asking you is now, whichever speaker you want, you just give me 5 minutes of the recording. For example, if you want Amitabh Bachchan's voice, you just give me 5 minutes of Amitabh Bachchan's audio sample and the text which you want Amitabh Bachchan to speak. That is sufficient for me to generate his own voice, is my claim, right? So that is the advantage of multi-speaker. Now, this concept is called as voice cloning. We are trying to clone someone's voice using our TTS engine, right? And yes, now again, the requirement has increased, saying that now I don't want to give an embedding, I don't want to give this. You do all the things which you want. I just will give you a prompt, because with the invent of LLMs, people are asking for prompt engineering. Like an example, I'll say, I want Amitabh Bachchan's voice speaking very politely, with a very low pitch tone, and this is the context he has to speak. You just generate this prompt and feed in as an input to my system. Then my prompt has to understand, hey, yeah, Amitabh Bachchan, pick the Amitabh Bachchan's encoder, neutral style, pick the neutral style. He want moderate pitch, take this style, and then this is the content. Feed that as this very same encoder as an input. So that is where your LLM comes into picture to actually configure your style TTS architecture. So that is where prompt-based TTS are very famous these days now. You got my point, right? So that is the only difference between prompt encoder and speaker encoder. Speaker encoder, directly you are telling that, hey, this is the reference audio, select this content and generate the audio. Prompt encoder, actually you are giving whatever your requirement in the form of text, like you are asking a human. My LLM takes that prompt, converts that into its latent representations E hat, and then generates that into config file, which configures my multi-speaker to generate the synthesized speech, right? And yes, so now here are few samples where the same sentence can be spoken with different accents. So suppose let me take male.
भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है। भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है। भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है।
So you can see, right, this is a ASR data where different domains data, different region speakers was taken, and these we have synthesized by just passing those speaker embeddings. Though these are scene speakers, but just for your understanding, I'm saying, so out of those 400, these are 6 speakers where you have different embeddings extracted.
भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है।
भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है।
भारत में उत्तर और दक्षिण की भाषाओं में काफी अंतर है.
So you have seen, right? The same sentence, different regions, again, male and female, speak it differently, right? So now this is the synthesized data for scene speakers. So that is where we call it as accent and dialect transfer. Then the actual voice cloning. If you see, this is the reference audio which we have passed in.
आज बदलते हुए समय में और कोविड प्रोटोकॉल्स की वजह से संग्रहालयों में नए तौर तरीके अपनाने पर जोर दिया.
Hello, I think I'm getting a lot of background noise. Hello? Yeah, sorry. Can I continue?
Yes, please.
Yes, please.
Yeah. So this is the reference audio which we have.
बदलते हुए समय में और कोविड प्रोटोकॉल्स की वजह से संग्रहालयों में नए तौर तरीके अपना.
So now if you see, this is again, we have just taken 15 minutes of this speaker's voice. I don't need to name him. I think everyone knew it. Yeah. And
आज बदलते हुए समय में और कोविड प्रोटोकॉल्स की वजह से संग्रहालयों में नए तौर तरीके अपनाने पर जोर दिया जा रहा है.
you can see, right, how much transfer. This is synthesized audio, and this is the reference audio which we have. So this multi-speaker has that capability of generating cloned voices. I think you might have seen a lot of YouTube videos generating Modi ji singing Telugu songs and all, right? So behind the scenes, this is what is happening. Yeah. So now, yeah, so far we have come to TTS, right? So you have text, you have generated, but post that what? There are a lot of industry standards. Again, they say we want studio quality because, hey, to generate uh, an audio advertisement or any geo advertisement, they just directly don't use output of TTS directly because it has inherent noise, right? That comfort is not there. So we just wanted to create enhancements, and if there are any noises in the data, we first need to remove that. So that is where you have something called denoising block, first which takes the noisy audio file and removes it, denoises it, and generates the denoised audio. And then there is an enhancement module which basically does bandwidth extension. So whatever data you have, it starts extrapolating and generating the more and more information and make it a rich content based speech file. So I have taken again some YouTube audio for you to understand.
ट्रेलर. एक विशाल समुद्री जहाज किनारे पे और उसके सामने पृथ्वी. प्रोडक्शन.
So if you see, this is some booth trailer audio which I have taken, which has a lot of background noise, music, and a speaker speaking, right? So once given to this unit denoiser, what it does is
ट्रेलर. एक विशाल समुद्री जहाज किनारे पे और उसके सामने पृथ्वी.
so the entire music, the background noises, and all were removed, right? And now here we have enhanced it using bandwidth extension techniques.
ऑफिशियल ट्रेलर. एक विशाल समुद्री जहाज किनारे पे और उसके सामने पृथ्वी. धर्मा प्रोडक्शन.
I hope you can feel the differences, right? So now this is the quality which they expect, and this is the quality which TTS gives. I mean, not exactly with these all noises and all, but just I think I want you to just visualize what all things we can do apart from TTS so that the content can become more richer and richer. Right? So these are few examples of different Indic language TTS models.
दुसऱ्याचा ढीग पाहून मला चक्करच आली आणि तिथे एक क्षणही थांबायला मन नाही म्हणलं. दुसऱ्याचा ढीग पाहून मला चक्करच आली आणि तिथे एक क्षणही थांबायला मन नाही म्हणलं.
So this is Marathi. Then similarly we have Kannada. Let me play Hindi.
हमारी टीम सुबह तक आगरा पहुंच चुकेगा. हमारी टीम सुबह तक आगरा पहुंच चुकेगा.
So these are before post processing, whatever style TTS gives as an output. And these are the post processing things which we actually denoise and then do an enhancement step. Right? Yeah. And now coming to the final part of the talk, which is called evaluations. So now how do we evaluate? We can't use any objective metrics, right? So there are two types at least. Let me cover
B, C,
first.
D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, W,
Who is that? Hello?
Yeah, please continue, Srinath.
Sure. Yeah. So now if you see here, the subjective metrics are, again, we have to measure the TTS engines with respect to naturalness, fidelity, intelligibility, and style, right? Whatever we have covered. Naturalness, how close it is to human voice. Fidelity, whether the robotic things are there, whether any that sparkling kind of sounds are there within TTS. Intelligibility, with respect to our information present in the data, how better the information can be extracted is intelligibility. And of course the style, the speaker style, how better we have captured the style. So these all variations need to be captured in these existing style TTS frameworks, unlike the earlier, because now objective metrics, if you see, people earlier what they used to do is they just used to get the audio, pass that to STT engine, generate word error rates, and whichever model gives best word error rate, they used to select that as a best model. But now, regardless of style, even if they say hi, how are you, or even if I say hi, how are you, my text is, I mean, my ASR engine will use me hi, how are you in the good text, because in both the things the intelligibility is good, right? May not be the style, may not be the naturalness, but intelligibility is good. And of course, my word error rate captures intelligibility. And again, perceptual evaluation of speech quality, PSQ, also tries to capture the fidelity and intelligibility, but not naturalness and style, right? So that is where the challenge comes in. And that is where what we have done is we have started the subjective evaluation in such a way that we have tried to generate the mean opinion scores with respect to each of the entity, like how natural it is. You have to rate the same audio file with respect to all four modalities in such a way. Yes, with respect to scale out of 0 to 5 or 1 to 5, you have to rate with respect to naturalness, you have to rate with respect to audio quality, you have to rate with respect to intelligibility, and you have to rate with respect to style, how good you are actually trying to capture. So this is how we started evaluating the TTS models. And then, yes, these are recent numbers after subject evaluation and whatever the existing models we have compared, the TTS models which were trained at Geo and with respect to all other existing competitors. So the blue line is the Geo, and you can see the other lines are with respect to other models, either open sourced or the enterprise versions. And then coming to the use cases, yes, content generation these days, that is the major use case where you have a text need to be spoken by a news anchor, because recently you might have seen a lot of news readers have come up, AI news readers, or they are calling it as AI readers in the native language. Odia already has launched a news channel with AI news anchor, replacing the human anchors. They just give the content and the anchor has to speak it. So this content generation became a very important use case in recent days. And then voice bot, yes, of course, every customer care, in order to improve their customer interactions, they need a proper voice bot which gives you a streamless endpoint where you can start interacting with it immediately without further diverging the topic, giving you answers accurately. So there you need both speech to text as well as text to speech. Bill reading, where there are blind people existing who can't read the bills or who doesn't know what is happening. At a click of button, if there is some use case or some entity which can read out your bill, saying that you have this much of amount, you have this much of balance. So that is one use case where TTS is trying to solve. And audio description. So recently you might have seen, right, lot of English movies, they have audio description, not just the actors in the movie are being spoken, but rather there will be a third descriptor who actually says how the actor's mood is, saying that in what scene they are, so that the visually impaired people can actually visualize what is happening along with the audio, right? Saying that yes, Shah Rukh Khan is wearing a white shirt, he's smiling, he's looking at this heroine. So these kind of descriptions are being actually generated using text to speech engines. So these are few use cases. And yes, one use case which I have already told, right? Content generation. So here you can see the human is an avatar, is not a human existing, it's an avatar. And then we have tried to generate an avatar with the very same TTS engine. So this is one content which we have generated for an example.
While the world eagerly waits for India's historic moment, the Indian Space Research Organization, or ISRO, has successfully reduced the orbit of Chandrayaan mission's lander module.
Yeah. So these are few content generation use cases, voice bot use cases and all. Yeah.
While the
Yeah, and yes, finally, this is the team. Before concluding, I just wanted you to introduce who all are involved on these TTS efforts, building all 12 Indic language TTS models in Reliance AICOE. So Bala, he's the lead, and myself and my team, Atava and Bhanu. Yes, with this, I want to conclude the talk. Thank you, and I'm open for questions. Any questions?
Hello, I had a question.
One small thing regarding related to your model while you are using it in online platform, means real-time platform, because you are using UNet as well as converting it to enhancement also you are doing.
Yes.
How it is performing in the real time means
No,
real
that's
time.
what. These all are additional features. As I said, right? These are needed for advertisements. But for example, if you want to use that in a voice bot or a IVR solution, there you need anyway 8 kilohertz sample frequency, right? We don't need to do bandwidth extension. So it is all customizable. We have the request parameter which we pass to TTS API, right? That has all these configurations needed. If you want it to generate an offline where you want high quality, so you take, for example, given a 100-word paragraph, you can take at least 5 to 10 seconds to generate. I have no problem, but I want a high quality output. Then you choose these parameters. But if you say I am okay because I am having only 8 kilohertz, because finally, even if you enhance using UNet and do enhancement post denoising, finally, if you are again downsampling it to 8 kilohertz, whatever bandwidth extension you have done, it's again being lost, right? So in those use cases, we will turn it off, where the latency currently is around 300 milliseconds for 100 words. So it is all dependent on the business with respect to which use case they are trying to solve. Did I answer your question?
Yeah, it's answering my questions. Thank you so much for, and it was a nice presentation. But I
Thank you.
also one thing I just need to ask, either you are using this is in the time series or as a spectrogram or mail spectrogram platform you are using for as an input.
Input is text, right? Input is
No,
always text.
while you are doing your enhancement and denoise, I think you need to take that.
Enhancement is spectrogram, not MEL. For
Okay,
denoiser, it is spectrogram. Yes.
okay. Thank you.
Because finally, for your unit, you need to measure this magnitude and phase part, right? Which can be extracted using spectrograms only. Yeah.
Okay. Also, you are using phase as well as magnitude. Those both are involved
Yes.
in.
Yes. Yes.
Okay.
Yes. I mean, you can. If interested, you can just go through Resemble Enhance. They have their GitHub repo as well. That is the one open sourced toolkit itself. You can just go through that.
Okay.
Yeah.
Yeah, I have a question.
Yes, sir.
In the MOS, based on 4 quantities, you compared GeoSystem with other systems, and
Yes.
one could see that Geo was definitely better.
No.
In which
Oh, can we?
language did you?
1 second. Let me share. No. Okay. S- Is my screen visible, sir?
Yes, this one. Yes.
So this is not with respect to each modality, because unfortunately all other competitors might not have all the modalities, right? They might have only single feature. So we have gone with the default setting where it is neutral text. Given a text, you generate neutral, right? What others are doing. With respect to English language, with respect to Hindi, with respect to Marathi, with respect to Tamil, Kannada, and Bengali, different languages. Different languages,
Oh,
single style.
okay, it was in the bottom language list. I see.
Yes.
Yeah, English, North Indian as well as South Indian languages. Yes, good.
Yes. And this is for internal purpose, because now for each language, these are the internal numbers. And we can say average of this might be these bars.
Okay.
Okay, any other questions from any other participants? Okay, so I think there is no question. So thank you, Dr. Sriram, for nicely explaining the recent technology in TTS and also focusing on how to enhance the noisy one. Okay. So Akhil, you have any questions?
Yes, sir. I had a
Yeah.
question.
Yeah, please go ahead.
Yeah, sir, actually in denoising, how does the system recognize like which is the sound and which is the required audio that is needed when like in the case both of them have similar intensities?
No, no, you have to train your model. See, that is what they might have intensity, but intensity is not the only thing which segregates it, right? You have a perception. How do we as a human segregate it? So in your training data itself, if you go through unit architecture, the input, that's what I'm saying, that magnitude and phase. Based on these components, you will tag your data saying that this is the speech and this is the noise, right? Even music, background noise, all these things are categorized as noise. The sound units, you actually have some formats involved, right? So based on that, you actually label your data in such a way that while training, you already know that, yes, these are my samples where speech is present. These are my samples or frames where noise is present. When I say noise, apart from speech, everything else is noise for me.
Okay, okay, understood. So there are like many more parameters other than intensity.
Yeah. Yes,
Oh,
yes.
okay, got it. Thank you.
I mean, it's not VAD. I think you are getting confused with voice activity detection. This is not VAD. This is enhancement module, denoiser. We are suppressing noise.
Understood.
Yes, I think Manisha also has some doubt. Go on.
Good
Hello,
evening, sir.
Manisha, you can go ahead.
Good evening, sir. Sir, I am a new PhD scholar doing PhD in TTS only. Sir, I want to know ki while training for single speaker, for example, Tekatron model, when to stop training?
That you have to follow your TensorBoard plots, right? You are using TensorBoard only, right?
Yes, sir. Yes, sir.
So you can just check your TensorBoard plots. Wherever your training loss and validation loss gets intersection. Matlab, see, your training loss decreases, validation loss decreases when your training happens, right?
Sir, in some cases, loss decreases, but we can't get attention plot.
No, I'm not talking about attention plot. If you go to TensorBoard plots, you have your training loss, validation loss plotted, right?
Yes, sir. Yes, sir.
Yeah, just go through your training loss plot, validation loss plot, overlap them. At some place, you will be able to see that your training loss still decreases, but your validation loss starts increasing. That is
Okay,
where
sir.
we say that the model is getting overfitted to your training data,
Yes, sir. Yes, sir.
right? So you have to stop at that merging point where your training loss and validation loss decreases. Make that point as your checkpoint and use that model.
Okay, sir.
Okay, so thank you, Dr. Sriram. So I think there is no question. So thank you once again for
Thank you.
accepting our invitation and delivering such a nice talk. Thank you. Thank you very much.
Thank you, sir. Thank you.
Thank you. With this, we come to the end of today's session. Tomorrow we'll meet at 6:30 p.m. Okay.